Welcome to Orbit Observer. It's lovely to have you here tonight. Wherever you are right now, settle in. Maybe you're under a blanket with the lamp still on. Maybe you've got a cup of tea going cold on the nightstand. Or you're on a train watching the dark slide past the window. Or you're just lying there in the quiet with your eyes already half closed. However you found your way here, I'm glad you did. So before we begin, tell me, where in the world are you watching from tonight? What time is it in your corner of the world? Leave it in the comments if you feel like it. I love reading them. And if you enjoy these slow journeys through the night sky, a quiet like and a subscribe really do help this sleepy little channel keep going. Small creators like me genuinely rely on it. It's the thing that lets these nights keep happening. And to those of you who already subscribed, who keep coming back, who let me keep watch while you drift, thank you, honestly. It means more than you know. Now, tonight, I'll try not to make this too interesting. That's the trade we always make here, isn't it? I'll do my best to keep things soft and slow, but if a little of it sneaks in and keeps you awake a while longer, well, at least you'll have learned something. A fair trade. There's no need to follow every word, no need to hold on to every number. If you drift off somewhere in the middle, that's perfectly fine. The ideas will still be here. The moon we're going to visit will still be there, turning slowly in the dark exactly where we left it. We're in no hurry at all. So let me start with something true. Something happening right now, somewhere very far away, while you lie here doing nothing more strenuous than breathing. Right now, out past Mars, out past the asteroid belt, around a planet so large it could swallow 1,000 Earths and barely notice, there is a small moon. And that moon is being squeezed. Not gently, not occasionally, constantly, relentlessly. Every single moment of every single day, a body slightly larger than our own moon is being kneaded by gravity like a fist closing around a piece of dough. And out of that squeezing comes heat. An astonishing amount of heat. Somewhere in the neighborhood of 100 trillion watts of it. Let that number sit for a moment, because it's a number that doesn't really fit in the mind on first pass. 100 trillion watts. Scientists usually phrase it as somewhere between 60 and 100 terawatts. A terawatt just being a trillion watts, a way of writing an enormous number without all those zeros trailing behind it. So picture 60 to 100 trillion watts of power pouring out of one small moon all the time without rest. Here's a way to feel that. All of human civilization. Every city lit up at night, every factory, every car and plane and phone and power plant, everything we build and burn and run across this entire planet. All of it together uses something like 18 to 20 terawatts. That's us. That's everybody. 8 billion people and all our machines adding up to roughly 20 trillion watts. And this one little moon is throwing off several times that. Not because anyone is feeding it fuel, not because anything is burning inside it, simply because it is being squeezed. That's the strange and beautiful thing I want to walk you through tonight, slowly. One gentle step at a time. Because the moon I'm talking about, its name is Io, is the most volcanically active world in the entire solar system. There are over 400 volcanoes scattered across its surface, and at any given moment, more than 150 of them are erupting. Lakes of molten rock wide enough to lose a city in. Fountains of sulfur reaching hundreds of kilometers up into space. A whole world that is, in a very real sense, on fire. And the question that hangs over all of it, the question almost nobody bothers to answer because the pictures are so dramatic that everyone just stops at the pictures, is a simple one. Where is all that fire coming from? Because here's the thing, it's not coming from inside. Let me say that again softly, because it's the heart of everything we're going to talk about, and I want it to settle in before we go any further. The heat that drives the most violent volcanism in the solar system is not coming from inside Io the way Earth's heat comes from inside Earth. Think about our own planet for a moment. The Earth is warm in its depths. Go down deep enough into the mantle, into the core, and it's hot. Hot enough to melt rock, hot enough to drive the volcanoes we have here. And where does that heat come from? Two main places. Some of it is leftover warmth from when the Earth first formed, 4.5 billion years ago. The heat of all that material crashing together and crushing down under its own weight, a kind of ancient fever the planet has never fully shaken off. And some of it comes from radioactive decay, from tiny amounts of unstable elements buried in the rock, quietly breaking down over billions of years and releasing little flickers of warmth as they go, primordial heat and radioactive decay. That's what keeps the Earth's furnace lit. Io doesn't run on either of those, not really, not primarily. A small moon like Io should have cooled off long ago. The leftover heat from its formation should have leaked away into space ages back. The trickle of radioactive warmth in its rocks is far too weak to explain even a fraction of what we see. By all the ordinary rules, Io should be a cold, dead, cratered little world, no more lively than our own quiet moon. Instead, it's the most geologically alive place we know of. And the whole reason, Hardy, is that it is being heated from the outside, by being squeezed, by being flexed, by gravity itself, working on it like hands working clay. We're going to take that apart very slowly tonight. This idea of heat from squeezing instead of heat from within. We'll look at exactly how the squeezing happens and why it never stops, and what keeps the whole thing wound up like a spring that can't unwind. We'll look at what all that energy looks like when it finally escapes. The lava lakes, the towering plumes, the strange snow that falls back down. We'll look at why this little moon has almost no craters when every other ancient surface in the solar system is pockmarked and scarred. And near the end, we'll find something quietly lovely tucked inside all this violence. The way the very same force that makes Io a kind of hell might, just a little farther out, be the thing that makes life possible somewhere else. Hell and home from one gentle squeeze. But that's for later. No rush. We'll get there when we get there. For now, let's just get our bearings. Let's find out where Io actually is and what it actually is before we set it on fire. So, Io, it's a moon. It orbits Jupiter, that giant striped planet you've probably seen in photographs, the one with the swirling bands of cloud and the great red storm bigger than our whole world. Jupiter is the largest planet in our solar system by a wide margin, a vast ball of gas and weather and crushing gravity, and around it circles a whole family of moons. Dozens of them, in fact, but 4 of them are large. 4 of them are worlds in their own right, and of those 4, Io is the closest in, the innermost. It rides nearer to Jupiter than any of its big siblings, deep in, close to all that gravity, which, as we'll see, turns out to matter enormously. Io is not tiny. People sometimes imagine moons as little pebbles, but Io is a real, substantial world. Its radius is around 1,821 kilometers, which, if that number means nothing to you lying here in the dark, just hold on to this. It's slightly larger than our own moon, the moon you've looked up at your whole life, the one that pulls the tides and lights the night. Io is a touch bigger than that. So when you picture it, don't picture a speck. Picture something the size of the moon or a little more, a genuine world with mountains and plains and lakes. It's just that the lakes are made of molten rock, and the mountains are taller than anything on Earth, and the whole surface is painted in colors that look like nothing you've ever stood on. Now those 4 big moons of Jupiter, Io, and 3 others called Europa, Ganymede and Callisto. They have a special name. We call them the Galilean moons, and they're called that because of who first saw them on a cold night more than 4 centuries ago. In January of the year 1610, a man in Italy named Galileo Galilei pointed a small, crude telescope up at Jupiter. By our standards, it was barely a telescope at all, a tube with a couple of lenses, the kind of thing a child might be unimpressed by today. But it was enough. And when Galileo looked through it at that bright point of light we call Jupiter, he saw something nobody had ever knowingly seen before. He saw little stars beside it, tiny points of light, arranged in a neat line, and over the following nights he watched them move. They shifted from one side of Jupiter to the other. They disappeared and came back. They danced around the planet in a way that only made sense one way. They were going around it. They were orbiting Jupiter. Now think for just a moment about how strange and how enormous that was, because in 1610, most people believed, were quite certain in fact, that everything in the heavens went around the earth. The earth sat at the center of creation, and the sun and the moon and the stars and the planets all wheeled obediently around us. That was the picture. That was how the universe was supposed to work, and a great many powerful people were deeply attached to it. And here was Galileo with his little tube of lenses watching 4 small worlds calmly circling something that was not the Earth. 4 moons going around Jupiter, paying our planet no attention at all. If things could orbit Jupiter, then the Earth was not the one fixed center of everything. The neat, comfortable Earth at the middle picture had a crack running straight through it. Those 4 little points of light helped topple an entire way of understanding the cosmos. They helped move us slowly, painfully out of the center of the universe and into our true place. One world among many, circling our own star, in a much larger and stranger arrangement than anyone had imagined. So the very moon we're visiting tonight, this furious little furnace of a world, was one of the 4 points of light that quietly rewrote our place in the heavens. It's been doing dramatic things for a very long time. We just couldn't see the details yet. The name itself, Io, comes from an old Greek story. In the myth, Io was a mortal woman, a young woman who caught the eye of Zeus, the king of the gods. And as these stories tend to go, that attention brought her nothing but trouble. To hide her from his jealous wife Hera, Zeus is said to have turned poor Io into a white cow, and Hera, not the least bit fooled, sent a gadfly to torment her, to sting and harry her without rest, driving her wandering across the world in endless misery. A figure in perpetual torment, never allowed to settle, never given any peace. It is, I have to say, an oddly fitting name for this moon, because as we'll see, Io the world is also a thing in eternal torment, squeezed and flexed and stung by forces it can never escape, never allowed to cool, never given a moment's rest. The people who named it probably didn't know how apt it would turn out to be. But it's a lovely little coincidence, isn't it? The tormented maiden and the tormented moon sharing a name across thousands of years. Just a bit of poetry to keep us company in the dark. Io moves quickly, by the way. It races around Jupiter in only about 1 3/4 days, 1.77 days to be precise. So a whole month on Io, a whole orbit all the way around that giant planet and back, takes less than 2 of our days. Round and round, again and again, closer and farther, and that constant racing around, that quick, tight orbit so near to Jupiter. Keep it in the back of your mind softly, because that motion is part of the engine. That motion is part of why Io can never cool down. But we're getting a little ahead of ourselves. Let's slow down again. Breathe. I want to tell you something now. that I think is one of the most quietly wonderful stories in all of science. And it's the kind of thing that sounds almost impossible when you first hear it, so I'll take my time with it. For a long, long time, nobody had ever seen Io up close. From Earth, even with our best telescopes, it was just a tiny dot, a pale speck beside the great bright disk of Jupiter. We knew it was there. We knew it was a moon, a little larger than our own, but we had no idea what its surface looked like. We couldn't make out a single feature on it. For all anyone could say, it might have been a cold, dead, grey ball, cratered and quiet like the moon overhead. That was the reasonable guess, honestly. A small moon far from the sun, far from any obvious source of warmth. Of course it would be cold and dead. Why wouldn't it be? And then, just before we got our first real look, 3 scientists sat down with nothing but mathematics, nothing but pencil and paper and the laws of physics, and predicted that Io would be a world of volcanoes. Their names were Stan Peele, Patrick Casson, and Ray Reynolds. Peele, Casson, and Reynolds. And in the year 1979, they published a short paper in the journal Science, one of the most respected places a scientist can publish, laying out an idea. They had been thinking carefully about Io's orbit, and about Jupiter's gravity, and about the tugs and pulls of the other moons. And as they worked through the numbers, they realized something. They realized that Io ought to be getting squeezed, that the constant flexing of its body driven by gravity should be generating heat inside it, a lot of heat. Enough heat, they reasoned, that Io's interior might be partly molten. Enough heat that its surface might show signs of widespread volcanic activity. Now, this was a bold thing to write down. Remember, at this point, nobody had ever seen a single volcano anywhere except Earth. Volcanoes were an Earth thing as far as anyone knew. To predict from pure mathematics that a little moon hundreds of millions of kilometers away should be covered in active volcanoes, that was a real leap. It was the kind of prediction that, if it turned out wrong, would have been quietly forgotten, and if it turned out right, would be remembered for as long as we do science. They closed their paper by suggesting that Io's surface might well show evidence of this widespread volcanism. They set the prediction down on paper, and they waited. They did not have to wait long, because at almost exactly the same time, within days, a spacecraft was arriving at Jupiter. A robotic explorer called Voyager 1, one of the great wandering probes we'd flung out across the solar system to see what was actually out there. Voyager 1 came sweeping past Jupiter in early 1979, in March, cameras rolling, sending its pictures back across the enormous gulf of space, photograph by photograph, a faint signal crawling home to Earth at the speed of light. And when those images of Io came in, the very first close-up images of that little moon any human being had ever seen, there it was. Not a grey, dead, cratered ball. Not the quiet world everyone had reasonably expected. Instead, a strange and lurid place, splashed with yellows and reds and whites and blacks, a surface like nothing anyone had laid eyes on before. And rising off the edge of it, caught against the blackness of space, were plumes, fountains, eruptions, material blasting up off the surface in great umbrella-shaped arcs hundreds of kilometers tall. Active volcanoes on a moon, erupting right there in the photographs for the very first time anyone had ever witnessed volcanism anywhere beyond the Earth. Just days after Peele, Casson, and Reynolds had predicted it on paper, I want you to sit with how remarkable that is here in the quiet. 3 people working with nothing but the laws of physics and the patience to follow the math wherever it led, said, that moon should have volcanoes. And then, almost before the ink was dry, a spacecraft arrived and showed us the volcanoes, exactly as predicted, erupting into space, It's one of the great called shots in the history of science, like calling your shot in a game, pointing to the far fence and saying the ball will land right there and then watching it sail over exactly where you pointed. They understood the world well enough from a great distance with no pictures at all to know what we'd find before we found it. And what they understood, the idea at the center of that prediction, is the very thing I've been circling around all this time. The squeezing, the flexing, the heat that comes from the outside, not the inside. They didn't predict Io's volcanoes by guessing that something was burning down in its core. They predicted them by understanding that Io was being kneaded by gravity, and that all that kneading had to turn into heat, and that all that heat had to go somewhere. So now you and I have an open question to carry forward into the rest of our slow journey tonight. We know what's happening. Io is on fire, 400 volcanoes, 150 erupting at once, plumes reaching hundreds of kilometers into the dark. And we know it isn't burning from within the way Earth burns. We know it's being squeezed. But how exactly? How do you heat a whole moon just by squeezing it? What does the squeezing actually look like down in the rock? What's doing the squeezing, and just as importantly, and this is the part I find most beautiful, what keeps it from ever stopping? Because here's a puzzle worth holding gently as you drift. Most things in the universe, given enough time, settle down. They find their balance, they wind down and grow quiet. A spinning top slows and falls. A swinging pendulum loses its swing. So why doesn't Io? Why has it been squeezed for billions of years without ever settling into peace? What keeps winding the spring? That's where we'll go next, slowly, gently, in just a little while. We'll feel out exactly how Jupiter's gravity grips this little moon and won't let go. We'll meet the unexpected partners in this whole affair, Io's own sibling moons, Europa and Ganymede, and the strange and elegant dance the three of them are locked into, a dance that turns out to be the real engine behind the engine, and we'll watch the solid ground of Io itself rise and fall, again and again by distances you'd hardly believe a planet's surface could move. But not yet. For now, just rest with the picture. A small moon, a little larger than our own, racing around a giant planet once every day, and 3/4 being squeezed so hard that it glows with the power of several human civilizations, throwing fountains of sulfur into the black. And 3 quiet scientists decades ago who saw it all coming with nothing but a pencil and the patience to do the math. There's no need to hold on to any of it too tightly. Let the numbers go soft. Let the names blur if they want to. The 100 trillion watts, the year 1610, the year 1979, Galileo and Peale and Voyager, none of it will run away. It'll all still be here, turning gently in the dark, whenever you'd like to come back to it. For now, just breathe and let yourself sink a little deeper into wherever you're resting. We've only just begun, and we've got a long, slow, beautiful way to go yet, you and I. Out past Mars, out past the asteroids, out to a little moon on fire in the dark. So let's begin where the story really begins, which is much closer to home than you might think. Wherever you are tonight, settled into your bed or curled on a couch with a blanket pulled up, I'd love to know where in the world you're listening from. It's one of my favorite things, imagining all the quiet rooms scattered across the planet, all the lamps still glowing softly, all of us drifting off together under the same stars. So if you feel like it, leave a little note and tell me where you are and what time it is in your corner of the night. And if these slow journeys help you find your way to sleep, a gentle like or a subscribe means more than you'd guess. This is a small, sleepy little channel, just me and my voice and a long dark sky, and small creators like me really do rely on your support to keep these going. To those of you already here, already subscribed, already part of this quiet nightly ritual. Ina, thank you. Truly, now settle in. Here is the thing I want to leave with you before we drift further out, the strange fact at the very heart of all of this. Right now, hundreds of millions of miles away, there is a little moon generating something on the order of 100 trillion watts of heat. Let that number sit there for a moment, soft and impossible. 100 trillion, or to put it another way, somewhere between 60 and 100 terawatts, depending on how you measure it. And our whole civilization, every city lit up, every factory humming, every car and plane and screen and stove on this entire planet, all of it together runs on something like 18 or 20 terawatts. So this one small moon all by itself is pouring out several times the power of everything humanity has ever built. And it isn't burning fuel to do it. There's no fire down there in the way we'd think of fire. There's no great furnace of coal or gas, no reactor, nothing being consumed. It's being squeezed. That's the whole secret. That's the spine of everything we'll talk about tonight. The heat doesn't come from within the way it does on our own Earth. Our planet stays warm inside, partly from the slow, radioactive decay of elements buried deep in the rock, and partly from leftover heat, the warmth of its own violent birth still trapped inside after 4.5 billion years. That's our kind of heat from within. But Io isn't kept warm by any of that. Io is kept warm from the outside by being kneaded over and over like a ball of dough in enormous invisible hands. And that single difference, heat from squeezing rather than heat from within, is the strangest and most beautiful thing about this little world. We'll come back to it again and again, because once you really feel it, everything else about Io falls into place. But before we go any further, let's just put this little moon somewhere. Let's give it a place to live in your mind, so it isn't just a name floating in the dark. Io is one of 4 large moons that circle Jupiter, the biggest planet in our solar system. 4 big moons, and Io is the innermost of them, the one orbiting closest in, nearest to that giant. The other 3, a little farther out, are Europa, then Ganymede, then Callisto, and we'll be hearing those names again, especially Europa and Ganymede, because they turn out to matter enormously to Io's story, even though they're so far away. But for now, just picture the 4 of them swinging around Jupiter in their wide, patient circles, with Io riding the innermost track. Io itself is not some tiny pebble of a thing. It's a real world, a little larger, in fact, than our own moon, where our moon has a radius of around 1,737 kilometers. Io comes in a touch bigger, around 1,821. So, if you've ever stood out on a clear night and looked up at the moon hanging there, full and silver and calm, you already have a pretty good sense of Io's size, just a little bigger than that familiar face. Only this one is anything but calm. These 4 moons have a name we still use today. We call them the Galilean moons, and that name carries a whole story inside it. Because back in January of the year 1610, more than 400 years ago, an Italian named Galileo Galilei pointed one of the very first telescopes up at Jupiter and saw 4 little points of light arranged in a neat line beside it. Night after night, he watched them, and he realized something that should have been impossible. They were moving. They were going around Jupiter. They were circling another world entirely, and not us. And that quiet observation, 4 faint sparks shifting in a telescope, helped bring down an entire way of seeing the universe. Because for a very long time, people had believed that everything, the sun, the planets, all of it, went around the Earth. That we were the center. And here was plain, undeniable proof that at least some things circled something other than us. 4 little moons going around Jupiter. The old cosmos, the one with us at its heart, began to come apart that very night. And the name Io itself comes from an old Greek myth the name of a mortal woman who was loved by Zeus, the king of the gods. A small, fitting name for a moon caught up in forces far larger than itself. So there it is, our little world, innermost of the four, a little bigger than our moon, discovered by Galileo in 1610, racing around Jupiter so quickly that it completes an entire orbit in just 1 3/4 days. Less than 2 of our days to circle that giant. Imagine that. While you sleep tonight, while you wake and go about your whole day tomorrow and lie down again the following night, Io will have gone all the way around Jupiter and most of the way around a second time. Round and round, fast and tireless, being squeezed at every turn. Now, I told you a moment ago about 3 quiet scientists with a pencil who saw it all coming. I want to give you that story properly because it's one of the loveliest things in all of science and a perfect thing to drift off thinking about. Picture the late 1970s. We had never seen Io up close, not really. It was a fuzzy little dot, a smudge of light, a name in a textbook. Nobody knew what its surface looked like. And in the year 1979, 3 researchers, a man named Stan Peel and his colleagues Patrick Casson and Ray Reynolds, sat down and did the math. They worked through the physics of what would happen to a moon like Io, squeezed the way Io is squeezed by Jupiter and its sibling moons. And the numbers told them something astonishing. All that flexing, all that kneading should be generating tremendous heat inside the little moon. So much heat that Io shouldn't be a cold, dead, cratered rock like our own moon at all. It should be alive with volcanoes. Their paper, published in the journal Science, ended by gently suggesting that Io's surface might show widespread signs of volcanic activity. A prediction made on paper from pure reasoning about a world no one had ever truly seen. And here's the part that gives me chills even now. Just days later, in March of that same year, 1979, a spacecraft called Voyager 1 swept past Jupiter and turned its cameras toward Io. And there, in those first close images, were enormous plumes rising off the surface. Volcanoes, erupting exactly as the math had said. The prediction and the proof arrived almost in the same breath, the pencil and the photograph just days apart. They had called their shot, and the universe had answered. So hold that picture as you sink a little deeper. A small moon, larger than ours, racing around its giant once every day and 3/4. A name from an old, sad myth. 4 faint lights that toppled a whole universe 4 centuries ago, and 3 patient people who, with nothing but reason and care, knew there was fire on a distant world before anyone had ever laid eyes on it. Now, let's talk about the heat itself. Because that's the real question, isn't it? Voyager saw the plumes. Peel, Casson, and Reynolds predicted them. But why? Why is there fire on this little moon at all? Why is a world out past the asteroid belt, far from the warmth of the sun, generating more heat than every power plant, every engine, every burning thing human civilization has ever made, all running at once? The answer is not what you might expect. If you think about a volcanic world, you probably think of something like Earth. And Earth is hot inside because of 2 things that happened long ago. When the solar system was young and still assembling itself, the violence of all those rocks and dust clouds colliding and falling together generated an enormous amount of heat. Some of that heat is still there, still slowly leaking out billions of years later. And layered on top of that is a second engine, radioactive elements in Earth's interior, unstable atoms quietly decaying, releasing energy as they fall apart, uranium, thorium, potassium, ticking away in the dark, warming the planet from within. These 2 sources, the leftover heat of formation and the slow tick of radioactive decay, are what drive Earth's volcanoes and tectonic plates and everything alive above them. Io doesn't work that way. Io is not hot because of anything inside it in that familiar sense. Io is not burning from the remains of some ancient collision, not warmed by decaying atoms the way Earth is. The heat inside Io comes from somewhere else entirely. It comes from the outside, it comes from the pull of other bodies, working on Io's solid flesh, bending and squeezing and kneading it, the way you might work a piece of dough between your hands. That process has a name. It's called tidal heating. And to understand it, you have to start with something you probably know, the tides. Here on Earth, the moon's gravity pulls on our planet as it orbits. It pulls on the oceans most noticeably, drawing them into a slight bulge on the side of the Earth facing the moon, and another corresponding bulge on the opposite side. Those bulges travel around the Earth as we rotate, and we experience them as the daily rise and fall of the tides. You may have seen them yourself if you've ever watched the water creep up a beach and then slowly retreat, leaving wet sand and small shells and the quiet smell of the sea. What's less obvious is that the moon's gravity also pulls on the solid rock of the Earth, not just the oceans, the ground itself. The actual bedrock beneath your feet gets deformed by the moon's gravity, stretched very slightly, raised very slightly, on each side of the planet. These are called solid body tides or land tides. Here on Earth, they're small, just a few centimeters, maybe a few tens of centimeters at most, not something you'd ever notice. You're not going to feel the ground shift under your feet when the moon is overhead, even though it does, just a little. But now imagine something far more powerful. Jupiter is not the moon. Jupiter is the largest planet in the solar system. Its mass is more than 300 times the mass of Earth, more than twice the mass of all the other planets combined. And Io orbits around this colossus not at the comfortable distance the moon keeps from Earth, but much, much closer, deep inside Jupiter's gravitational grip. So Jupiter does to Io what the moon does to Earth, but on a scale that belongs to a different category of reality altogether. Jupiter's enormous gravity reaches into Io's body and raises a tidal bulge, not in an ocean. Io has no oceans. In the solid rock itself, the crust, the mantle, the deep interior, all of it gets pulled toward Jupiter, drawn slightly out of shape into a very faint elongation, a subtle stretching, like holding a ball of soft clay and pressing gently at one end. The side of Io facing Jupiter is pulled a little toward it. The side facing away is pulled a little in the other direction, in the same way Earth gets that second tidal bulge on its far side. Io becomes ever so slightly oval, a tiny egg shape instead of a perfect sphere, pointed toward and away from Jupiter. If Io's orbit were perfectly circular, this would be a stable, unchanging thing. The bulge would point toward Jupiter always like a finger eternally reaching, and there would be very little heating. The shape would be fixed. No flexing, no friction, no fire. But Io's orbit is not perfectly circular. It is slightly elliptical, slightly oval in its own right. Not dramatically so, not like a comet swooping far out and then plunging close, just a little, just enough. And this means that as Io moves along its orbit, its distance from Jupiter changes. When it's a little closer, Jupiter's gravity pulls a little harder, and the tidal bulge grows a little taller. When Io moves farther away, the pull relaxes, and the bulge settles back down ever so slightly. And all the while, Io is also spinning, so the bulge isn't pointing exactly at Jupiter the whole time. It's constantly being tugged to realign, so the rock is never at rest. It flexes. The solid ground of Io, not just a thin veneer, but the whole interior, kilometers deep, is being constantly deformed, squeezed and released, as the little moon swings around its orbit once every day and 3/4. And here is the key, the thing that turns a physics lecture into something you can feel. When you squeeze something repeatedly, it generates heat. Think of bending a wire back and forth, until the bent spot grows warm between your fingers. Think of kneading bread dough and feeling your hands grow warm after a while. The deformation creates internal friction at a molecular level. Atoms and crystal structures being pushed past each other, resisting, generating tiny amounts of energy as heat each time. In a body the size of Io, with a force the size of Jupiter's gravity doing the squeezing, those tiny amounts add up to something staggering. Estimates of Io's total heat output vary depending on how you measure it and which models you trust, and the numbers range across a substantial spread. But broadly, the best estimates suggest Io is generating somewhere between 60 and 100 terawatts of power from tidal heating. Some estimates push even higher. To make that real, consider this. All of human civilization, every city, every factory, every car and plane and ship and data center and light bulb, every heating system and cooling system, every hospital and home, the entire planet's combined energy use amounts to somewhere around 18 to 20 terawatts. Io is generating several times that, purely from being squeezed, not from any fuel, not from any burning, just from the gravitational flexing of its own body over and over, orbit after orbit, without pause, without rest. That heat has to go somewhere. And where it goes is up, out through the crust, through whatever pathways of weakness exist, out through vents and fissures and channels of melted rock, out through hundreds of volcanic centers distributed across a surface that looks from a distance a little like a bruised and terrible piece of fruit. The heat escapes, and the escaping is what we call volcanism. The volcanoes aren't the cause of anything, they're just the exit. But there's a question hiding inside all of this, and if you're still awake enough to notice it, I think it's the most important one. If the heating comes from Io's orbital eccentricity, from the fact that its orbit is slightly oval rather than perfectly round, then why doesn't the orbit just fix itself? Orbits left alone tend to circularize over time. The same tidal interaction that flexes Io and generates all that heat also acts as a very gentle brake, pulling the orbit toward roundness. If you waited long enough, Io's orbit should settle into a circle. The flexing would slow down, the heat would drop, the volcanoes would quiet, the moon would become still, dead, and covered in craters like everything else out here. So what's stopping that from happening? The answer is Io's siblings. Io is not alone in its orbit around Jupiter. Jupiter has 4 large moons. The ones Galileo Galilei saw in January of 1610, the ones that crept across the face of that giant over weeks of cold nights in Padua, the ones whose movement told him something true and radical about the order of the cosmos. These 4 are called the Galilean moons, Io closest in, then Europa, then Ganymede, then Callisto, each a world in its own right. And 3 of them, Io, Europa, and Ganymede, are locked together in a gravitational arrangement so tidy it almost looks designed. For every one orbit that Ganymede completes around Jupiter, Europa makes exactly 2. And for every one orbit Europa makes, Io makes exactly 2. So when Ganymede goes around once, Europa goes around twice, and Io goes around 4 times, 1 to 2 to 4. This is called the Laplace resonance, named for the French mathematician Pierre-Simon Laplace, who worked out its mathematics in the 18th century. And it's not a coincidence, it's not something that happened by chance. The 3 moons drifted into this relationship through their gravitational interactions and are now locked there, each one's orbit stabilized by the others. And what the Laplace resonance does to Io is extraordinary. Because of the rhythmic gravitational tugs from Europa and Ganymede, each arriving at predictable times in predictable directions, Io's orbit is kept from circularizing. Every time Io's orbit starts to round out, every time the tidal braking tries to fix the ellipse and calm the flexing down, Europa comes around and gives Io a little gravitational nudge, just enough to re-excite the eccentricity, maintain the oval, keep the flexing alive. Europa and Ganymede are, in a sense, Io's torturers, or perhaps its furnace attendants. They keep the fire going not by adding fuel, but by making sure the squeeze never stops. If you could somehow remove Europa and Ganymede from the equation, freeze them in place, or magic them away, Io's orbit would gradually circularize over geological time, the tidal flexing would fade, the heat would drop, and eventually Io's volcanoes would go quiet. The most volcanically active world in the solar system would die. The fire would go out. Instead, the resonance holds, and so the flexing continues orbit after orbit for as long as the solar system endures, the siblings keeping the little moon kneaded and burning in an endless cycle that has gone on for billions of years and will go on for billions more. If you've been lying in the dark imagining any of this, I hope you've come to the part where the rock itself is moving. Because the solid ground of Io doesn't just get warm from all this, the ground physically rises and falls every single orbit. Here on Earth, as I mentioned, the moon's gravity produces land tides. Tiny deformations of the solid crust, centimeters in height. They're real, measurable by sensitive instruments, but far too small for any human body to detect. The Earth beneath you moves, but you will never feel it. On Io, the numbers are different. The best tidal deformation models suggest that the solid surface of Io, or the actual rocky ground, rises and falls by something on the order of 100 meters every orbit. 100 meters, that's roughly 330 feet, 30 stories, the height of a fairly tall building. And this isn't ocean water sloshing, this isn't a storm surge or a flood, this is rock, the solid ground of another world, flexing like a slowly breathing chest, 300 feet up and 300 feet down, over and over, every day and 3/4, in the crushing grip of Jupiter. Think about that for a moment, because it puts the volcanism in a different light. You're not just heating a rock from the outside and waiting for it to melt at the edges. You're working it, physically working it, the way a blacksmith works iron, the way a baker works dough. The interior of Io is not passive in this process. It is being physically deformed on a cycle, and the friction of that deformation is the engine. The heat is a byproduct of the work being done, and when you run numbers like those through the physics, what comes out the other end is not a few warm spots and some gentle seeping of lava. What comes out is hundreds of volcanoes. So let's talk about what hundreds actually means. The title of this video promises something startling. The James Webb Space Telescope looked at Jupiter's moon, Io, and found hundreds of volcanoes erupting at once. That is true in the sense that it reflects Io's documented, established state. But it's worth being honest about what the numbers represent, because the truth is actually more remarkable than any single dramatic count. Over decades of observation, starting with Voyager in 1979, continuing through the Galileo orbiter that spent years in Jupiter's neighborhood in the 90s and early 2000s, supplemented by ground-based telescopes, and then Juno and JWST in recent years, scientists have catalogued more than 400 volcanic centers on Io's surface. 400 identified locations where volcanic activity of some kind has been detected or inferred. And of those 400, at any given moment, the estimates suggest that roughly 150 or more are active at once, not dormant, not resting, active. That figure isn't a single snapshot from one telescope pass. It's the standing baseline, the ground truth of what Io is, confirmed and reconfirmed by every instrument that has ever looked at it carefully. When James Webb added its infrared eyes to that record, it wasn't discovering something new in the sense of something unexpected. It was giving us a new chemical and thermal window into what had always been there, confirming active eruptions, characterizing the heat and the gases with a precision no previous observatory could match, seeing the fingerprints of sulfur chemistry from Io's volcanic breath with extraordinary clarity. Hundreds of volcanoes erupting at once is not an anomaly. It is not an event. It is Io on a Tuesday. And the energy driving all of those hundreds of eruptions, all of that activity, all simultaneously, day and night, in the dark and in the cold between the planets, is the squeeze, the tidal flexing, the sibling resonance. 100 trillion watts generated not by anything burning, but by the physical bending of a moon. Now, what does that energy look like when it escapes? Io's gravity is low, not as low as our moon's, but low. About 18% of what you feel standing on the Earth's surface. If you could somehow stand on Io, which would be extremely inadvisable for reasons we'll come to, you would weigh about a fifth of what you do now. A person who weighs 150 pounds on Earth would weigh about 27 on Io. Things fall slowly. Things fall gently. And Io has almost no atmosphere to speak of. A thin, patchy wisp of gas, mostly sulfur dioxide, clinging to the surface in some places and nearly absent in others. Nowhere near enough to slow anything down significantly. This matters enormously for what happens when a volcano erupts. On Earth, volcanic eruptions produce plumes, certainly, but the atmosphere pushes back. Gravity pulls back. The plume rises to some altitude, sometimes dramatic, sometimes reaching the stratosphere, and then it spreads and thins and eventually settles back. On Io, there is almost nothing pushing back and almost nothing to thin out into. Material ejected upward by a volcanic eruption doesn't fight its way through a dense atmosphere. It simply goes. It follows a long, graceful ballistic arc through the near vacuum, rising and rising, slowing only under Io's gentle gravity, until it reaches the peak of its arc and begins to fall back. Plumes on Io have been measured rising as high as 500 kilometers above the surface. 500 kilometers. That is roughly the distance from one major city to another in many parts of the world. It is the altitude at which some satellites orbit the Earth, and it is happening off the surface of a moon smaller than our own, driven not by some unusual or special event, but simply by the ordinary outgassing of sulfur and sulfur dioxide from lava too hot to contain it. Because these plumes are not made of steam, there is no water involved. Io is not a wet world, not a drop of liquid water on the surface, not as far as we know, not anywhere in this inferno. The plumes are driven by sulfur and sulfur dioxide, SO2, which exists on Io's surface as frost in many regions, painted there by the fallout of previous eruptions. When hot lava flows across that frost, or when superheated rock vaporizes the sulfur at depth, the sulfur and sulfur dioxide flash instantly into gas. They expand violently, exactly the way water flashing to steam drives a geyser here on Earth, but sulfur instead of water, sulfur dioxide instead of steam. The gas carries rock fragments and fine particles with it as it jets upward, and the whole mixture fountains out through the vent and into the near vacuum above. It rises, it spreads. In the low gravity, with no air to resist it, it forms what observers have described as an umbrella shape, a great spreading fountain that peaks and then cascades outward and downward in a broad, slow arc, a fountain hundreds of kilometers tall with a footprint on the surface that can span hundreds of kilometers wide. And when the material falls back, it settles, it coats the ground. And because the material is rich in sulfur compounds, and because sulfur produces different colors depending on its temperature and form, and the way it's been altered by radiation and heat, the settled fallout paints Io in a palette unlike anything else in the solar system. Yellows from sulfur in various states, whites and pale grays from sulfur dioxide frost, reds and oranges, some of the most vivid in the solar system, from short-chain sulfur compounds or sulfur that has been altered by the radiation environment, and blacks, the dark tones from recent lava flows, fresh basaltic rock still hot and barely cooled, cutting across the brighter colors like ink spilled on a page. The surface of Io seen from space looks like something between a bruised pear and a fever dream. Every color is a record. Every shade tells you something about what happened there, how recently, how hot, what chemistry was involved. The surface is a ledger of eruptions, and it is being rewritten constantly. Every single day, material is being deposited, frost is being laid down, lava is cooling and darkening, the surface is changing, not slowly, the way surfaces on most worlds change, not on timescales of millions or billions of years. On Io, the change is measured in human lifetimes, in decades, sometimes in years, sometimes in the days between one spacecraft visit and the next. We can see it. Between the time Voyager saw Io in 1979 and the time the Galileo orbiter was studying it in the mid-1990s and early 2000s, features had changed noticeably. Regions that appeared one color had shifted. Deposits that hadn't been there before had appeared. Lava flows that showed up as dark marks in one image were absent in another, taken years earlier. The surface was never the same twice. This is not a dead world. This is not a relic. This is a living, restless, endlessly renewing place, and every volt of the energy that drives that renewal comes from the gravitational grip of a gas giant planet and the orbital rhythm of two sibling moons. That squeeze never stops, and so the volcanoes never stop, and the sulfur keeps falling, and the colors keep painting, and somewhere in the dark between the planets, this little tortured moon keeps breathing, keeps burning, keeps going. Just hold that thought, settle into wherever you are, the bed, the blanket, the dim room, and let the image come to you slowly. A world not much bigger than the one that hangs in our own night sky, racing around a gas giant so large it dwarfs every other planet combined, laced with hundreds of volcanic vents all exhaling at once, plumes rising so high they'd brush the edge of space if they were happening here, the ground itself rippling up and down 30 stories with every orbit. The surface painted in sulfur yellows and lava blacks, and the pale frost of SO2 settling out of fountains no telescope on Earth could have imagined before we sent machines out to look. And beneath all the spectacle, beneath the plumes and the colors and the impossible numbers, one quiet physical fact. Squeeze something enough and it gets hot. That's it. That's the whole engine. Jupiter squeezes Io. Io heats up. The heat escapes as fire. It is, in a strange way, one of the most elegant things in planetary science. A gravitational machine, precise and relentless, converting orbital geometry into heat, converting heat into volcanism, converting volcanism into a painted, churning, never-resting world on and on and on at the edge of the solar system's main real estate, in the long, cold dark beyond the asteroid belt. And we didn't have to go there to know it was happening. We figured it out, first, with nothing but a pencil. That never stops being remarkable to me. So now you have the engine. You understand what's generating the heat, why it doesn't stop, what keeps the orbit from calming down, and what the escaping energy looks like when it breaks free at the surface. Plumes of sulfur 500 kilometers tall, hundreds of volcanic centers firing at once, a surface repainted by eruption fallout in colors that vary by the day. But some of those volcanic features are more than just vents. Some of them are something altogether harder to picture, harder to put into ordinary terms, harder to hold in the mind without it slipping away. One of them is the size of a small country. And it is not a mountain, and it is not a crater, and it is not exactly like anything that exists on Earth. It is a lake of lava, and it has been there, active, boiling, overturning itself for as long as we've been able to look. Its name is Loki Patera. And when we get there, in just a little while, when you're ready, the numbers are going to ask something of your imagination. But there's no hurry. Take a breath. Let the image of the plumes settle, 500 kilometers of sulfur rising in slow arcs through a vacuum, the umbrellas spreading, and the frost coming down like snow in colors that don't belong to any winter you've ever seen. We have time. Let's talk about the mechanism itself, not just that it happens, but how. Because once it clicks, once you feel the logic of it, Io stops being a curiosity and becomes something almost inevitable. A moon that could not, by the laws of physics, as they apply in that particular corner of space, be anything other than what it is. Jupiter is enormous. You already know this in the abstract. Our biggest planet in the solar system, more than 1,300 Earths would fit inside it. But knowing a number and feeling a gravitational field are different things, and Io, sitting just inside Jupiter's front door, feels it in a way that nothing we've ever visited quite parallels. What Jupiter's gravity does to Io is raise a bulge, a tidal bulge like the one the moon raises in Earth's oceans, except here there are no oceans. What's being raised is rock. Solid rock, mantle and crust, pulled and distorted by a gravitational field that doesn't ask permission and doesn't take no for an answer. The rock on the side of Io facing Jupiter is pulled toward Jupiter a little more than the rock at the center, and the rock at the center is pulled a little more than the rock on the far side, and the result of that difference, that gradient, is a stretching, a slight elongation along the Jupiter-facing axis. A bulge in the body of the moon itself. On Earth, the moon does something similar. Land tides, the solid crust of our own planet rising and falling in response to the moon's gravity, do exist. They're real. They're just not very large. The solid Earth moves by something on the order of tens of centimeters, maybe 30 or 40 centimeters at most, through a full tidal cycle. Enough to measure with precise instruments, not enough to feel. On Io, that number is different by a factor that will take a moment to absorb. The solid surface of Io rises and falls by up to 100 meters every single orbit. 100 meters, roughly 330 feet, a 10-story building appearing and disappearing in the rock, over and over, every 1.77 Earth days. The ground itself, not water, not atmosphere. The ground, the actual crust and mantle of a world, breathing in and out by the height of a skyscraper, continuously without pause, because Jupiter never stops pulling and Io never stops moving. And here is the part that transforms this from a strange fact into a physical explanation. If Io's orbit were perfectly circular, the bulge would still exist, but it would be fixed. It would point at Jupiter, constant, and Io would rotate in a way that kept the same face toward the planet, tidally locked as our moon is locked to us, and the bulge would sit still. No shifting, no flexing, no friction. But Io's orbit is not circular. It's elliptical, slightly but measurably, and the ellipse doesn't come from some ancient accident that will gradually smooth out. It is maintained actively, continuously, by Io's siblings, Europa and Ganymede, the second and third of the Galilean moons. These three worlds are locked into what's called the Laplace resonance, named for the French mathematician Pierre-Simon Laplace, who worked out the mathematics of it in the 18th century. The ratios are tidy enough that once you hear them, you find yourself wondering how they got there. For every one orbit Ganymede completes around Jupiter, Europa completes exactly 2. And for every 2 orbits Europa completes, Io completes 4. 1, 2, 4. Over and over, locked in that rhythm, these 3 moons passing and tugging at one another at the same points in their orbits, again and again, like dancers in a very old and very precise choreography. And that rhythm keeps Io's orbit from settling. Left alone, without its siblings, Io's orbit would gradually circularize. Tidal forces would smooth it out. the ellipse would shrink, the bulge would stop shifting, the flexing would cease, and Io, geologically speaking, would go quiet, cold, dark, cratered eventually, like every other old surface in the outer solar system. But Europa and Ganymede do not leave it alone. Their gravitational tugs arriving at the same predictable points in the orbit, again and again, keep Io's path just elliptical enough. They prevent the healing. They hold the eccentricity in place, which means they are, in a very real sense, the reason Io's volcanoes still run. Remove the resonance, remove the siblings, and within some geological time frame, the fires go out, the surface stills, the plumes fall back. Europa and Ganymede are not innocent bystanders in what happens to Io. They are the engine behind the engine, the reason the squeeze never stops. So, Io moves nearer to Jupiter, the bulge grows. Io swings further away, the bulge shrinks. The bulge shifts direction as the geometry changes, and rock, real, solid, mantle rock, flexing back and forth through a 100-meter range with every orbit, generates friction. And friction generates heat. The numbers are, again, the kind that require a moment of stillness to receive properly. Best estimates of Io's total heat output from this mechanism sit somewhere between 60 and 100 terawatts. The uncertainty comes from the difficulty of the measurement. Io's volcanic activity is not perfectly uniform, and calibrating an infrared budget from spacecraft instruments at varying distances is genuinely hard science. But even the conservative end of that range is worth sitting with. All of human civilization, every city, every factory, every data center, every car and ship and aircraft, every light left on in every apartment in every country on Earth right now, consumes energy at a rate of roughly 18 to 20 terawatts. That is the entire energetic footprint of our species on this planet. Io radiates several times that purely from being squeezed, not from nuclear reactions, not from radioactive decay building up over billions of years the way Earth's interior is still warmed by elements like uranium and thorium breaking down in the deep mantle. That's how Earth stays geologically active, internal heat, left over from formation and supplemented by decay, leaking out slowly. Io's mechanism is almost the reverse. The heat is not coming from inside in that slow, ancient sense. It is being generated fresh, continuously, by an external gravitational relationship, and it has to go somewhere. It goes up. And this is where the surface stops being abstract. Io has more than 400 identified volcanic centers. Not 400 mountains with craters on top in the Earth volcano sense. 400 volcanic features. Lava lakes, calderas, active flow fields, plume sources, regions of ongoing eruption or persistent high heat. Of those, somewhere upward of 150 are estimated to be active at any given time. When you hear the phrase hundreds of volcanoes erupting at once, that is what it means. It is not a single night snapshot from a telescope. It is Io's baseline condition documented across decades of observation by Voyager, by the Galileo orbiter, by ground-based telescopes with adaptive optics, by Juno, and now by the infrared sensitivity of the James Webb Space Telescope, which can resolve the chemical signatures of what's coming out of those vents. The sulfur dioxide, the forbidden emission lines that mark what's burning and what's venting and what's freezing back onto the surface between eruptions. Hundreds erupting at once is not hyperbole. It is carefully and honestly understood just a description of what the place is. And the energy escaping through those 400 centers does not leave quietly. Io's gravity is low, about 18% of Earth's, roughly 1.83 meters per second squared. When volcanic material is launched upward, there is simply much less gravity pulling it back. And because Io has almost no atmosphere to speak of, a thin patchy layer of sulfur dioxide that is more of a vapor suggestion than a true sky. There is nothing to slow the ejecta down, nothing to scatter it, nothing to hold it close to the ground. The plumes go up and up and up. The largest documented plumes on Io have risen to heights of roughly 500 kilometers above the surface. 500 kilometers. The edge of what most definitions would call outer space begins about 100 kilometers above Earth's surface. Io's volcanic plumes reach 5 times that height, erupting into what is effectively vacuum, following long ballistic arcs, spreading into the umbrella shapes that Voyager's cameras caught in 1979, and that have since been imaged in extraordinary detail by every mission that's passed by since. These plumes are not steam. There is no liquid water on Io, no ice vaporizing in volcanic heat the way geysers work on Enceladus. The propellant is sulfur and sulfur dioxide, vaporized by contact with lava that in some locations reaches temperatures exceeding 1600 Kelvin, hotter than any volcano currently active on Earth, flash boiled into gas and hurled outward under pressures that shoot material hundreds of kilometers into nothing. And then it falls. The sulfur and sulfur dioxide that goes up must come down. It does across enormous areas, landing as frost. As snow, in a sense, except the colors are wrong for any snow you've imagined. Sulfur dioxide frost is white. Sulfur, in different molecular configurations, produces shades of yellow and red and orange, and occasionally almost black. The surface of Io is painted by its own plumes continuously, the colors shifting in real time as new eruptions deposit new material and old material weathers under radiation. Yellow sulfur plains, red sulfur rings around persistent plumes, white sulfur dioxide frost in the colder regions, dark lava flows cutting through all of it, still warm, still moving in places, cutting new paths over old ones that were themselves cut over older ones, all the way down through a history of eruption that goes back as far as Io has existed in this orbit under this gravitational pressure. There are no craters visible in any of this, or almost none, and that absence is its own kind of testimony to what the heat is doing, and we'll come to it. The story of a surface that cannot hold its scars, a world that heals itself not because it is peaceful, but because it never stops erupting long enough for the scars to show. But first, a lake. Not a lake the way you're imagining one, not blue, not still, not reflecting a quiet sky. This one is made of lava. It is roughly 200 kilometers across, about the distance from one mid-sized city to the next if you were to drive it, a journey of a couple of hours on a motorway. Except this is not a road. This is an open surface of molten silicate rock, a shallow bowl of it, sitting on a world where the ground itself rises and falls 100 meters every orbit, where plumes of sulfur rise 500 kilometers into an airless sky, where the total volcanic output exceeds the entire energy budget of human civilization by several times over. The lake is called Loki Patera, and it is the single most powerful volcanic feature in the solar system. Loki Patera sits on Io's northern hemisphere, a roughly crescent-shaped depression that planetary scientists classify as a patera, a term borrowed from Latin for a shallow bowl used in ritual offerings, because the shape, seen from above, has that same wide, spread quality. An opening, a basin. In this case, a basin filled to an indeterminate depth with lava, rimmed by dark shores and covering an area larger than many of the well-known lakes on Earth. Lake Erie, for comparison, is about 388 kilometers long. Loki Patera, at around 200 kilometers across, is in the same order of magnitude. You could fit a significant body of water inside it. Instead, it holds fire, and the fire is not quiet. That is the thing about Loki Patera that makes it so strange and so riveting to the researchers who have spent careers watching it from Earth and from orbit. It does not simply sit there and glow steadily. It pulses. It brightens, then dims, then brightens again, on a cycle that repeats roughly. And the roughly is important because nature is not a clock, roughly once a year. Sometimes a little shorter, sometimes a little longer. But the pattern is recognizable enough that scientists watching Loki Patera from ground-based telescopes have been able to track it, predict portions of it, and debate what causes it for decades. The leading interpretation is something genuinely extraordinary. The surface of Loki Patera, the part you would see if you were somehow hovering above it, which you would not survive, but if you were, is not uniformly liquid. It has a crust. As the lava cools at the surface, even slightly, it forms a thin, hardening skin, dark and glassy, like the skin that forms on custard or cooling chocolate left on a counter. But this crust is not stable. It is denser than the liquid lava beneath it, and so eventually it sinks. Not all at once, and not uniformly across the whole 200-kilometer basin. The current model suggests the process sweeps around the lake progressively. One edge of the crust founders and sinks, new hot lava wells up behind it, and the foundering advances around the lake like a slow wave, a kind of rolling over, a cycle of the surface consuming and renewing itself. When the fresh hot lava is exposed in a section of the lake, Loki Patera brightens in the infrared because the newly exposed material is radiating heat. When the crust has largely recovered and thickened, it dims, and then it happens again. It is a lava lake that periodically eats its own surface, and it does this on a schedule that, from several hundreds of millions of kilometers away, scientists watching from Earth can follow. JWST looked at Loki Patera. That new infrared eye, orbiting at a point in space far beyond the Moon's orbit, trained itself on Io and detected the chemical and thermal signatures coming off this feature and others. The sulfur dioxide, the emission lines from compounds driven off by the heat of eruptions. JWST can read the chemistry of what Io is exhaling in ways that ground-based telescopes and even earlier spacecraft could not match in terms of sensitivity and wavelength range. It is not adding craters to the map or sending back close-up photographs of the shoreline. What it is doing is giving planetary scientists a new kind of window, a chemical window, into the processes running at full power on Io's surface right now, in real time, as you listen to this. That window confirms what the cascade of prior observations had suggested. Loki Patera is not a quiet feature between eruptions. It is continuously active. The heat coming off it, even in its dimmer phases, is detectable. The gases it emits are measurable. The most powerful volcanic feature in the solar system does not take days off. But Loki Patera, for all its extraordinary scale, is only one of Io's faces, and some of the others are quite different in character. There is a place called Pele. Named for the Hawaiian goddess of volcanoes, Pele is one of Io's persistent hotspots, a volcanic center that has been erupting in one form or another for as long as spacecraft have been watching. But Pele is not famous for a lava lake, it is famous for what it leaves behind. Pele produces a plume, and that plume, over time, has deposited a ring of sulfur compounds around itself that stretches approximately 1,200 kilometers across. That is the diameter of the ring, not the radius, 1,200 kilometers. If you were to place that ring over a map of Europe, it would be reaching from one coast toward the interior of an entire continent. The ring is red, a distinctive dark red, almost rusty in some images, caused by short-chain sulfur molecules, the particular chemistry of what Pele specifically vaporizes and ejects. The color is genuinely unusual. Most of Io's surface tends toward yellows and whites and oranges, the colors of sulfur and sulfur dioxide in their more common configurations. But Pele's ring has this dark red quality that makes it recognizable in global images of Io. Even at low resolution, you can pick it out. It is one of the most distinctive features on Io's surface, not a mountain, not a crater, not a lava flow, but simply the accumulated drift of millions upon millions of ejections, the downwind record of a vent that has been running for an extraordinarily long time, painting its signature color onto the ground in a circle more than 1,000 kilometers wide. And then there is Tvashtar. Tvashtar is another of Io's volcanic centers, and it has produced some of the more dramatic imagery that has come back from spacecraft visiting the Jovian system. Named for the Hindu artisan god, the craftsman of the gods, the maker, Tvashtar has been observed in various states of activity. But the image that many planetary scientists think of when they think of Tvashtar is the one captured by the New Horizons spacecraft. New Horizons was launched in January 2006, headed for Pluto, the first mission specifically designed to reach the outer solar system's most famous dwarf planet and the Kuiper Belt beyond. It was a long journey, and on the way, in February 2007, New Horizons made a flyby of Jupiter, not a primary target. A gravity assist, using Jupiter's enormous mass to bend its trajectory and add velocity, slinging it further and faster toward Pluto. But while it was passing through the Jovian system, it turned its instruments toward Io. And Tvashtar was erupting. The images New Horizons returned showed a plume rising approximately 330 kilometers above Io's surface. 330 kilometers. The umbrella shape of it, the characteristic form of Io's larger plumes, where material launches outward in all directions and the edges of the curtain are lit against the blackness of space, was clearly visible. It looked honestly less like what you think of when you think of a volcanic eruption on Earth, and more like something from a painting of an alien world, which of course it is. A vast, translucent fountain frozen in a single image, its material in the act of falling back toward a surface that had already erupted it once and would absorb it and likely erupt it again. 330 kilometers. The cruising altitude of the International Space Station above Earth is about 400 kilometers. Tvashtar's plume was reaching most of the way there, and it was being driven, as all of Io's plumes are driven, not by water vapor, not by steam the way Earth's geysers or even some of its volcanic eruptions involve water, but by sulfur and sulfur dioxide. These are the propellants on Io. When lava contacts sulfite or sulfide minerals in the surface rock, or when it encounters pockets of sulfur dioxide frost near the surface, the sulfur and SO2 vaporize almost instantly, the way water flashes to steam if you drop it on a very hot pan, but vastly more energetically. And the expansion of that gas is what drives the plume upward into that low-gravity, nearly atmosphere-free sky. So the plumes are, in a sense, sulfur geysers on a scale so far beyond anything a terrestrial geyser can manage that the comparison almost breaks under the weight of the difference. But the underlying physics, a liquid or solid vaporized by heat and propelled through an opening by the pressure of expanding gas, is genuinely analogous. Old Faithful in Yellowstone reaches about 55 meters on a good day. Tvashtar reached 330 kilometers. And Pele's plumes have been observed reaching estimates of around 300 kilometers as well, with the maximum measured plume heights on Io running up toward 500 kilometers in the most energetic events. The material that goes up in those plumes eventually comes back down, and what comes back down is not liquid. By the time the sulfur and sulfur dioxide has traveled hundreds of kilometers out into Io's near vacuum, at the temperatures of space, it has cooled and condensed into solid particles, into frost, into a kind of snow that drifts down across enormous areas surrounding each active vent. The white regions of Io's surface, and there are broad, bright white areas, are largely sulfur dioxide frost. The yellows and reds are different allotropes, different molecular configurations of sulfur itself. And wherever the surface has been painted recently by a plume, you can read the eruption in the color, in the distribution of the frost, in the subtle chemistry of what a particular vent has been producing. It is a world that is painting itself continuously, without pause. And the thing about a world that is continuously painting itself is that the older paintings get covered, new layers go over the old ones. And this is where we arrive at one of the most striking things about EOE, something that, when you really sit with it, tells you something profound about how active this world truly is. There are almost no impact craters on Io. None, or very close to none. Depending on the survey and the resolution of the imaging, scientists working through the Voyager and Galileo datasets found essentially 0 confirmed impact craters on Io's surface. In a solar system that has been bombarding everything with asteroids and comets and smaller projectiles for 4.5 billion years, in a system where every other old surface, the Moon, Mercury, Callisto, the ancient highlands of Mars, is saturated with impact craters, some of them enormous, some layered on top of each other across billions of years of accumulated collisions. Io has almost none. Think about what that means. The Moon is right there, visible from your window on any clear night, and its surface is covered in craters. Some of them are billions of years old. They've been sitting there, largely undisturbed, because the Moon has no weather, no significant volcanism, no geological processes running at any meaningful rate to erase them. The craters accumulate, they layer, they persist. The same is true of Callisto, one of Jupiter's other Galilean moons. Its surface is ancient, saturated with craters, a kind of deep time record of the outer solar system's violence. And then there is Io, right there in the same neighborhood, just as ancient in terms of when it formed, subject to the same bombardment history as everything else in the solar system, because the asteroids and comets don't care which moon they're hitting. But its surface has no craters, or almost no craters. They hit, and then they disappear, buried by lava flows, covered by plume fallout, reshaped by new eruptions before the impact scar has any time to become a fixed feature. The resurfacing rate that achieves this is estimated at something between roughly 1/10 of a centimeter and a centimeter or more of new material deposited globally per year on average. That range is approximate, and the distribution is anything but uniform. Right next to an active vent, the deposition rate is far higher, and in quieter regions it's lower. But averaged across the whole surface, if you think about what a centimeter of new material per year means over millions of years, you start to get a sense of the accumulated depth of the churning. In 1,000,000 years, that's potentially 10 kilometers of new material. In Io's case, spread unevenly, with some of it recycling back into the interior, the effect is not 10 kilometers of accretion. It's continuous overwriting. The surface is being erased and rewritten on timescales that are, in geological terms, essentially instantaneous. The result is that the surface of Io, the actual ground, the material you would be standing on if you were there, which again you would not survive, but the material itself is geologically extremely young, far younger than almost any surface anywhere else in the solar system. The Moon's Maria, the dark volcanic plains on our own satellite, are mostly 3 to 3.5 billion years old. Mercury's youngest volcanic plains are still ancient by any ordinary measure. The surface of Io, by contrast, is being renewed at a pace that makes its average surface age not billions of years, but orders of magnitude less. Some of the lava flows visible from orbit are years old, some are decades, some are hundreds of thousands of years at most. Your driveway, if you have one, was probably poured sometime in the last several decades. Concrete has a lifespan of 30, 40, 50 years with reasonable maintenance. The surface of Io, in many places, is geologically younger than that. A world 4.5 billion years old wearing a surface that in places is essentially brand new, because it cannot stop erupting long enough for anything to age. This is what the absence of craters is telling you, not that Io is somehow protected from impacts, not that the solar system has been gentle with it. It has been hit many times by the same projectiles that hit everything else. The craters simply don't last. The evidence is buried before it can become permanent. What you are seeing when you look at the surface of Io, whether in images from Galileo or the Juno flyby photographs from 2023 and 2024, or in the infrared maps JWST is building, is not a record of the past. It is almost entirely the present, the recent past, and the near future. A surface in the act of being made right now, at this moment, as you listen. And here is where it gets stranger still, because the lava that is doing this remaking, the lava covering up the craters, building up the plains, erupting through the vents, and painting the surface in sulfur colors, is not ordinary lava. Not ordinary in the sense that ordinary lava on Earth, the kind that flows from Kilauea or Etna, is made of basalt, a silicate rock that erupts at temperatures of roughly 1100 to 1200 degrees Celsius. Hot, destructively hot. But within a range we understand. Io's lavas, in at least some locations, appear to be hotter than that, significantly hotter. Temperature measurements from the Galileo spacecraft's NIMS instrument, its near-infrared mapping spectrometer, came back with values in some active regions exceeding 1600 Kelvin. That is roughly 1300 degrees Celsius and higher in some estimates. Hotter than the basalt that comes out of virtually any currently active volcano on Earth. What does lava that hot correspond to? The question pulls you back in time because Earth has had this kind of lava. Not recently, not in the last several hundred million years, but in the Archean eon, the deep past, when Earth was younger and its interior was hotter from the residual heat of formation and from the early days of radioactive decay before a significant portion of those radioactive elements had decayed away. In those ancient oceans of the early Earth, there were eruptions of a type of lava called komatiite. Komatiite? The word comes from the Komati River in South Africa, near the rocks where this ancient lava type was first formally studied. Komatiite flows erupted at temperatures that current estimates suggest were between 1600 and 1900 degrees Celsius or higher, substantially hotter than basalt. The lava was so fluid at those temperatures that it flowed in a very particular way, leaving behind distinctive crystalline textures in the rock, patterns that geologists can still read in 3.5 billion-year-old outcrops in places like Australia and Canada and South Africa. Earth has not produced komatiite volcanism for a very long time. The interior has cooled. The conditions that generated it no longer exist here. But on Io, the conditions may exist now. The temperature retrievals from Galileo and the ongoing thermal measurements from ground-based adaptive optics observations and now from JWST's infrared sensitivity suggest that at least some of Io's volcanic centers are erupting material at temperatures consistent with this ancient, ultramafic, high-temperature style of volcanism, not basalt. Something closer to what Earth was doing when it was young and hot and raw. This makes Io something peculiar and valuable in the catalogue of things we have studied in the solar system. It makes Io a working model, not a fossil record, not a geological archive you read in ancient rocks, but an active, real-time demonstration of a style of volcanism that occurred on Earth billions of years ago and that we can otherwise only study from the frozen crystalline ghosts it left behind in South African river valleys. If you want to know what the early Earth's volcanic output might have looked like, if you want to understand how those ancient komatiite flows behaved, how they spread, how hot they were at the surface, what they did to the landscape. Io may be showing you, not perfectly, not identically. Io is not Earth, and the specific chemistry and tectonic context differ. But the temperatures overlap. The style of eruption may overlap. The scale of heat flux pouring out of a body through volcanic activity rather than through plate tectonics may overlap in meaningful ways. A world in the outer solar system, heated not by decay from within, but by being squeezed from outside, running hotter than any volcano currently active on Earth, may be showing us what our own planet was doing in the Archean, when the first single-celled life was barely getting started in the primordial oceans, and the land above them was being constantly resurfaced by flows of lava we can barely imagine. There is a quietness in that thought if you let it settle. The hellscape and the origin story running together. The most violent body in the solar system as a kind of mirror held up to the moment when Earth was beginning. And the violence on Io is not only expressed in liquid lava and erupting plumes, it is also expressed strangely in solid rock. In mountains, Io has mountains that are in some cases taller than anything on Earth, and they got there by a process that is uniquely Ionian, uniquely a product of exactly the forces we have been describing, the relentless resurfacing, the constant addition of new material, the buried layers accumulating. The tallest of Io's known mountains is called Volcanoes Montes. The name is pronounced roughly Bohuch Osor, and the feature is a collection of peaks, a massif, really, rising to roughly 17 to 18 kilometers above the surrounding terrain. Mount Everest, Earth's tallest peak measured from sea level, is just under 9 kilometers. Volcanoes Montes is approximately twice as tall, and it is on a world that has no plate tectonics. On Earth, the tallest mountains exist because tectonic plates collide. The Himalayas, the Alps, the Andes, these are collision zones, places where enormous sections of crust are being pushed against each other, one diving under the other, or the two crumpling at their meeting point, pushing rock upward in the process. Plate tectonics is a driver of mountain building, and Earth has it running more or less continuously, so there are always some mountains in the process of being built somewhere on the planet. Io does not have plate tectonics. Io does not have a global system of moving crustal plates. Its crust is not divided into sections moving around on a flowing asthenosphere the way Earth's is, and yet it has mountains twice as tall as Everest. How? The answer, again, comes back to the resurfacing. That continuous deposition of new material, that the lava flows, the plume fallout, the steady accumulation of layer on layer on layer, is not without consequences for the crust beneath it. All that material has weight. As new layers accumulate at the surface, they press down on what's below them. The crust is being loaded from above continuously by its own volcanic output. And a crust that is being loaded from above must go somewhere. It can't compress indefinitely in the vertical direction. The rock at depth is under increasing pressure, and at some point, the stresses within the crust resolve themselves by faulting, by the rock cracking along fault planes and large blocks of it being thrust upward, displaced vertically by the accumulated pressure of the material above. The crust is being squeezed not by plate collision, but by the weight of its own volcanic accumulations, and the squeezed blocks pop upward, building mountains. Mountains built by being buried, not mountains built by collision, not mountains built by a mantle plume pushing up a dome, but mountains built because the surface is accumulating so much new material so fast that the older crust beneath has nowhere to go but up along fault lines, faulted blocks, thrust skyward by the compression of their own burial. This is a geological process that doesn't have a clean analog on Earth, because Earth's resurfacing doesn't happen by the same mechanism at anything like the same rate. But on Io, it is apparently capable of producing peaks nearly twice the height of Everest. Buzor Le Montes and the other mountain ranges on Io rise to heights that dwarf anything on our planet, built not by the drama of continental collision, but by the quieter, relentless, decades-long and centuries-long accumulation of lava and frost, pressing down until something has to give, and a block of old, deep crust is thrust into the sky. And on that sky, those mountains sit without any of the erosional forces that wear Earth's mountains down. There is no rain on Io, there are no glaciers in the ordinary sense, no ice made of water. There is sulfur dioxide frost, but the erosional forces it can generate are different. The mountains, once built, can persist in their extraordinary heights in a way that mountains on Earth cannot. They are not being worn away by weather. They are being buried, slowly, by the continued fallout of the volcanism that built them. So even the mountains on Io are a product of the heat. Everything on Io is a product of the heat. The mountains, the lava plains, the plume deposits, the absence of craters, the patchy sulfur dioxide atmosphere that freezes onto the ground at night and sublimates back into gas by day. All of it traces back to the same engine, the squeeze, the tidal flexing, the orbital eccentricity kept alive by the gravitational conversation between Io and Europa and Ganymede, the 1-2-4 resonance that ensures the orbit never rounds out and the flexing never stops. If you removed the orbital resonance, if somehow Europa and Ganymede ceased to exist, or their orbits shifted out of that precise ratio, Io's orbit would gradually circularize. The tidal bulge would stabilize, the flexing would diminish, the frictional heating would slow, and over some span of time the volcanoes would quiet, the plumes would fall, the lava lakes would cool and crust over, and eventually solidify. The mountains would stop being built. The surface would begin to accumulate impact craters, slowly, the way every other old surface in the solar system does, slowly building up the record of bombardment that Io currently lacks. Without the resonance, Io would become Callisto. Old, cratered, quiet. A memory of early solar system violence preserved in ancient rock, rather than a live demonstration of violence ongoing. But Europa and Ganymede are there. They are not going anywhere. The resonance has been running for a very long time, and the best models suggest it is stable, not something that is about to break down or shift. So the torture continues, the heating continues, the volcanoes continue, and a moon the size of ours, orbiting a gas giant more than 300 times Earth's mass, goes on being the most volcanically active body in the solar system, not because of anything inside it, but because of the precise gravitational geometry of the place it occupies in this system. Heat from squeezing, not from burning. The distinction matters, and not just for Io. The resonance that keeps Io's orbit eccentric is the same resonance that keeps Europa in an orbit that is also slightly elliptical, also tidally flexed, also heated from within by the same mechanism. Europa does not erupt, its surface is frozen, but below that frozen surface, tidal heating is depositing energy into the ice and rock. And the leading scientific consensus, supported by a wide body of observation and modeling, is that below Europa's icy crust there is a liquid water ocean, not a small pond. An ocean, possibly deeper than any ocean on Earth, kept liquid by the same tidal flexing that is running far hotter and far more violently on Io. Europa's tidal heating is gentler because Europa is farther from Jupiter, and the eccentricity forced on it by the resonance is smaller. But the mechanism is identical. The force that makes Io a hell, that buries its craters, raises mountains twice as tall as Everest, drives plumes 500 kilometers into the sky, and fills a lava lake 200 kilometers across, is the same force attenuated by distance and geometry, that may be keeping a vast liquid water ocean warm and liquid in the dark beneath Europa's ice. Hell and habitability, the same physics. One expression of it is the most violently volcanic surface in the solar system. Another expression at a different distance, with a different interior composition running at a lower intensity, may be one of the most promising environments in the solar system for the chemistry that we associate with the possibility of life. That is not a small thing to hold in your mind as you drift towards sleep tonight. The same gravitational squeeze, the same orbital resonance. Pointed one direction, it builds a world of fire and sulfur and mountains thrust up from their own burial. Pointed another direction, at a moon made partly of water ice, it might be slowly warming an ocean that has never seen sunlight, in the dark below a frozen sky, on a world we have not yet fully seen. And yet the story of Io does not stop at what you can see on its surface. At the plumes and the lava lakes, and the color-soaked plains and the mountains rising improbably against the dark of space. Because there is a whole other chapter happening below, in the interior of this small, tortured, endlessly churning world. And what scientists have found down there, or more precisely, what they have inferred down there because no spacecraft has gone inside Io, and none will for a very long time, is in its own quiet way just as strange as anything on the surface. Io is a differentiated body. That is a specific term from planetary science, and it means something important. When a rocky world is born and grows hot enough in its early life, the materials that make it up begin to sort themselves by density. The heavy stuff, iron sulfide, sinks toward the center, pulled inward by gravity. The lighter, silicate rock rises toward the outside. The world separates into layers like oil and water settling in a jar. It becomes a structured thing, a core, a mantle above the core, and a crust above the mantle. Io did this. Gravity measurements from the Galileo spacecraft, which orbited the Jupiter system from 1995 to 2003, allowed scientists to work out Io's moment of inertia, a way of gauging how mass is distributed through a body's interior. And what those measurements told them was that Io has a substantial core of iron and iron sulfide, possibly at least partly molten, sitting at the center, surrounded by a silicate mantle wrapped in that vivid volcanic crust we have been talking about all along. So Io has an inside, a middle, and an outside, like Earth, like Mars, like our own moon. In that sense, Io is not exotic at all. It is a perfectly ordinary, differentiated, rocky world. Except that it is also being heated from the outside continuously at a rate of somewhere between 60 and 100 terawatts, and that heat has to travel upward through the mantle and out through the crust. And how it does that, exactly how and where the tidal heat is being deposited, and how it moves, is one of the genuinely open and lively puzzles in planetary science right now. Here is where it gets interesting, and where honesty requires a careful step. One of the things the Galileo spacecraft carried was a magnetometer, an instrument designed to measure magnetic fields. Jupiter has an enormous, powerful magnetic field, one of the strongest in the solar system, and as Galileo flew past the Galilean moons, it used its magnetometer to probe whether those moons generated or disturbed that external field in distinctive ways. For Io, what the magnetometer data suggested, in an analysis led by Krishan Khurana and colleagues, was something remarkable. The pattern of the magnetic field perturbations near Io was consistent with what you would expect if Io had a global layer of electrically conducting liquid somewhere in its interior. Not a magnetic field generated by Io itself, something subtler, an induced field, a response to Jupiter's rotating magnetic field of the kind you would get if there were a shell of conductive material, something like molten rock, wrapped around the core. This is how we found evidence for liquid water oceans on Europa and Callisto as well, using the same Galileo magnetometer data. The principle is the same. A rotating external magnetic field induces currents in a conductive layer, and those currents produce a secondary field that Galileo could detect. For Europa and Callisto, the conductor is thought to be a salty liquid water ocean. For Io, the conductor would have to be something different, something that can exist in the extreme thermal environment of a moon being heated to extraordinary temperatures by tidal flexing. The leading candidate is a layer of partially molten silicate rock, magma, forming a global shell within the mantle, not a pool, not a pocket. A layer, possibly wrapping all the way around the core, of hot, partially molten, electrically conductive rock. Scientists sometimes call this a magma ocean, though that phrase can conjure images more dramatic than the reality may be. The term covers a range of possibilities, from a deep layer that is largely molten with some solid material floating or sinking through it, to a hot, partially molten zone, sometimes called an asthenosphere. Rock so close to its melting point that it behaves almost like a thick fluid over geological time, even if much of it is technically still solid. The honest position is this: the Galileo magnetometer data are consistent with a global conducting layer inside Io, and a deep, hot, partially molten layer of rock is the most natural explanation in a world being heated at the rate Io is. But whether it is a true global magma ocean in any dramatic sense versus a hot, partially molten mush of rock and liquid is still actively debated. The Galileo measurements were not designed primarily for this purpose, and interpreting induced magnetic fields is not a simple task. It is a leading hypothesis, a strong one, supported by the physics of tidal heating at Io's scale. But it is not yet a settled fact. What makes the question matter is this: if Io does have a deep global layer of partially molten rock, then tidal heat is being deposited there, in the deep interior, and it rises through the mantle and drives the volcanism from below. That picture, deep heating, upwelling through the mantle, erupting at the surface, would be one way of understanding how Io works as a system. But there is a puzzle, a nagging, elegant, unsolved puzzle. If you look at where the tidal flexing should be generating the most heat, and you can model this using the mathematics of how a viscoelastic body deforms under a time-varying gravitational stress, the models suggest that certain regions of Io should be hotter than others. The heat production should have a geographic pattern. And when you look at where Io's volcanoes actually are, the hottest and most active volcanic regions don't perfectly match what the simplest tidal heating models predict. Some of the hottest observed regions are offset from where the models say the heating should peak. The volcanoes are not quite where the equations say the fire should be. This mismatch has been studied carefully. It may mean that the tidal heat is generated deep in the mantle and then transported horizontally before it erupts, that the interior shuffles the heat around before it reaches the surface. It may mean that our models of Io's interior structure and rheology, in the way the rock responds to stress, are not quite right yet. It may mean that the geometry of the Laplace resonance produces heating patterns more complex than simple first-order models capture. Nobody has fully resolved this. It is, as of now, an active area of research, one of the open mysteries that keeps planetary scientists awake, which feels, in a sleep video about the most volcanic world in the solar system, like a small irony worth acknowledging gently. The honest picture of Io's interior is, we know it is differentiated. We have strong evidence of a substantial core. We have suggestive evidence for a deep, hot, partially molten layer driving the volcanism from below. And we have an unsolved puzzle about the exact geography of where tidal heat is deposited and how it gets from there to the surface. Io is not a finished story. No place in the solar system is. And now the scale opens up. Because Io is not just a volcanic world sitting quietly in orbit around Jupiter. Io is connected to Jupiter in ways that make the whole system feel more like a single, living, electrically charged organism than a planet and its moon. Every second, not every year, not every day, every second, roughly a ton of material is being stripped from Io. Not knocked off by asteroid impacts, not slowly evaporating away into nothing, actively stripped. Ripped from Io's thin atmosphere and from its surface by the radiation environment and by the electromagnetic forces around Jupiter, and flung out into space around the planet. A ton a second, picture, if you like, holding a large bag of sugar in each hand, roughly a kilogram each. Now imagine that happening 1,000 times every second, continuously, day and night, year after year, century after century, for billions of years. That is material from Io's volcanoes, mostly sulfur and sulfur dioxide, rising as gas through the eruptions and the plumes, reaching the thin atmosphere, and then being swept away by Jupiter's overwhelming magnetic environment. And that material does not simply disperse, it collects. It organizes itself into a vast, donut-shaped ring of charged particles that circles Jupiter at roughly Io's orbital distance. Scientists call this the Io plasma torus, plasma, the fourth state of matter after solid, liquid, and gas. When atoms are stripped of their electrons, ionized by the radiation near Jupiter, the result is a soup of charged particles, ions and free electrons that respond to magnetic fields rather than just to gravity. The sulfur and oxygen atoms ripped from Io become ionized in Jupiter's intense radiation belts. And those charged particles spiral along Jupiter's magnetic field lines, concentrating into a torus, a donut, around the planet. You cannot see the Io plasma torus with your eyes any more than you can see a magnetic field, but spacecraft can detect it, and it is enormous. The torus glows in ultraviolet light. It carries more mass than you might imagine. It is energetically significantly a feature of the Jupiter system as real and as consequential as the Great Red Spot or the ring system of Saturn, just invisible to ordinary sight. And the connection between Io and Jupiter does not stop there. Io is electrically linked to Jupiter by a structure called the Io flux tube. The name is accurate in the most literal possible way. It is a tube of magnetic flux, a bundle of Jupiter's magnetic field lines that runs between Io and Jupiter's upper atmosphere, and through that tube electric current flows, not a trickle, not a modest charge. Millions of amperes continuously. For reference, the largest electrical generators on Earth, the turbines of great hydroelectric dams, produce on the order of thousands of amperes. The Io flux tube carries millions. It is as if Io and Jupiter are connected by an invisible electrical cable, thicker and more powerful than anything human civilization has ever built, and that cable is simply part of the fabric of the Jovian system. The current in the flux tube accelerates charged particles down toward Jupiter's poles, where they slam into Jupiter's upper atmosphere and produce auroras. Not the kind you see on Earth. Shimmering green curtains of light on a quiet winter night, excited oxygen atoms at the edge of space. These are Jupiter's auroras, vast, intense, ultraviolet bright structures that would be invisible to your eyes but which spacecraft see clearly. And within those auroras there are specific bright spots, footprints they are called, that mark exactly where the Io flux tube connects to Jupiter's atmosphere. You could look at Jupiter's aurora and find Io's footprint, a small, persistent, bright spot running ahead of and behind the position of Io in the sky, tracing the path of the flux tube as Io moves in its orbit. Io 500,000 kilometers away, leaving its mark in Jupiter's light. Io is not simply a moon, it is an electrical generator, it is a particle source, it is a plasma fountain. It sits at the center of an electromagnetic system that extends across hundreds of thousands of kilometers of space, that lights up Jupiter's poles, that fills a torus around the largest planet in the solar system with ionized gas from its own volcanic eruptions. The same volcanoes, the same plumes, the same lava lakes and sulfur-painted plains. All of it, the eruptions, the stripped material, the plasma torus, the flux tube, the auroral footprints, is one connected system driven by the same tidal squeeze that heats the interior, that builds the mountains, that buries the craters. Io is not a world apart. Io is a dynamo, and Jupiter is what it powers. And there is one more thing about Io's immediate environment that deserves a quiet moment, because it is one of those small details that, once you hear it, makes the world feel both more real and more strange. Io has an atmosphere. A thin one. Patchy, variable, nothing that would protect you or let you breathe, but an atmosphere nonetheless. Its main constituent is sulfur dioxide, the same gas that smells sharp and unpleasant near a struck match, the same chemical that Io's volcanoes pour into space in such quantities. SO2 is how planetary scientists write it, one sulfur atom bonded to two oxygen atoms. This atmosphere is sourced continuously from the volcanic eruptions and from something subtler. The surface of Io is partly coated in frozen sulfur dioxide, the same snow that falls from the plumes settling back onto the ground in layers of yellow and white frost. When sunlight falls on that frost, some of it sublimates. It goes directly from solid to gas, the way dry ice does when you take it out of a cooler without passing through a liquid phase. And that sublimation feeds the atmosphere from the ground up, a slow seeping of gas from the frost into the air above. But here is the part that stops you. When Io passes into Jupiter's shadow, when Jupiter eclipses the Sun as seen from Io's surface, the sunlight disappears. The sublimation stops, and the atmosphere, no longer fed by sublimating frost, begins to collapse. The SO2 gas in the air cools and starts to freeze back onto the ground. Literally, the atmosphere freezes. It settles back down as frost onto the surface it came from until the shadow passes and the sun returns. And then, when sunlight touches the frost again, the atmosphere breathes back into existence. The frost sublimates, the gas rises, the air returns, an atmosphere that collapses and reforms with every shadow, a world whose sky falls and rises as it moves through the dark and the light of its orbit around Jupiter. And all of this happens inside one of the most hostile radiation environments in the solar system. Jupiter's magnetic field traps high-energy particles, electrons and protons and heavier ions, accelerating them to enormous energies and concentrating them in bands around the planet. Io orbits deep inside these radiation belts, far closer to Jupiter than even the innermost belt that would be dangerous for a spacecraft. The radiation near Io is lethal to humans in ways that should not require much elaboration. If you stood on Io's surface, setting aside the volcanoes, the sulfur dioxide snow, the lack of breathable air, the lava that might be flowing nearby, and the atmosphere that occasionally disappears, the radiation dose you would receive would be enormous, many times the threshold for acute radiation sickness. Io is not visited, it cannot be visited in any human sense. The Galileo spacecraft itself, which studied Io in extraordinary detail over the course of multiple flybys, was being slowly destroyed by the radiation each time it flew close. The mission planners had to ration Io's flybys carefully, limiting exposure to protect the spacecraft's electronics for as long as possible. Galileo eventually died in 2003 when NASA deliberately plunged it into Jupiter's atmosphere, partly to prevent any risk of it crashing accidentally into Europa, which might carry the chemistry of life, and contaminating it with microbes that might have survived the journey from Earth. So Io is observed from a respectful distance whenever possible, and that makes the recent visits all the more striking. In late 2023 and early 2024, NASA's Juno spacecraft made a series of close flybys of Io, passing within roughly 1,500 kilometers of the surface. 1,500 kilometers. For context, that is about the distance from London to Istanbul or from New York to Miami. In space terms, this is extremely close, close enough to see detail, close enough to resolve volcanic features that no human eye and no spacecraft had examined at this resolution in more than 2 decades. The last time anything had come this close to Io was during the Galileo mission, which ended in 2003. For over 20 years, Io had been observed from a distance, its surface mapped from afar. And then Juno came. Juno was not originally designed as an Io mission. It arrived at Jupiter in 2016 to study the planet's interior, its atmosphere, its magnetic field, and its auroras. The same auroras lit partly by Io's plasma torus and flux tube. But as Juno's primary mission wound down and NASA extended it, the spacecraft was given new targets, including Io. The images that came back were extraordinary. JunoCam, with a wide-angle camera on Juno originally designed for public engagement, for the sheer visual beauty of the Jovian system, captured Io in detail that has not been seen before. Volcanic features resolved sharply. And among the things that Juno's instruments found was something unexpected in its clarity. Some of Io's lava lakes, seen from close range, have surfaces that are almost mirror-smooth. Not churning, not turbulent, smooth. Specular is the scientific term, meaning that light reflects off the surface at precise angles, the way it does off a mirror or a still pond, rather than scattering in all directions the way it does off rough ground or choppy water. The surface of some of Io's lava lakes, under certain conditions, appears to be a thin, solid, or nearly solid crust of cooled lava floating on molten rock below, still enough and flat enough to reflect light like a mirror. This is not simply an image of volcanic violence. It is an image of something stranger, quietness on top of what lies below, a skin of calm over a furnace. Lava lakes on Earth can also develop glossy, mirror-like surfaces when the crust has cooled just enough. The lava lake in the Halema-Umau crater at Kilauea in Hawaii, before the 2018 eruption drained it, sometimes showed this quality, a dark, glossy surface that reflected the glow from below. But a lava lake 200 kilometers across with a mirror surface you can see from 1,500 kilometers above is something else again. Juno also saw mountains, the mountains of Io, rising with nothing to explain them in the conventional geological sense. There are no tectonic plates on Io. None of the mountain-building processes that shape the Himalayas or the Andes are operating there. And yet the mountains exist. Bosal Montes, the tallest of the known Io mountains, rising to roughly 17 or 18 kilometers above the surrounding plains, taller than Mount Everest by a factor of nearly 2. The mechanism is, in its own way, a direct consequence of the same relentless resurfacing that erases Io's craters. As volcanic material falls continuously from the plumes and from lava flows, it buries everything. It adds layer after layer on top of what was there before. And this constant accumulation of mass on the surface puts the crust under enormous compressional stress, squeezing it, pressing it in from the sides as new material piles on top. Eventually, something has to give, and what gives is the rock itself. Great slabs of crust compressed beyond their limit crack and tilt and are faulted upward, thrust up from below by the pressure of all that accumulated weight pressing in. The mountains of Io are built not by plates crashing together, but by the crust being crushed under its own burial, squeezed upward by the pressure of its own death. A mountain built by drowning. There is something almost poetic in that. And now, alongside Juno, there is another eye on Io, a newer one with a perspective that no telescope before it could provide. The James Webb Space Telescope, JWST, studies the universe primarily in infrared light. Infrared is the light of heat. Everything with a temperature above absolute zero radiates infrared, and the hotter it is, the brighter it glows in infrared wavelengths. Webb was designed to look at the very early universe, at galaxies so distant and so ancient that their light has been stretched by the expansion of space into infrared wavelengths. But its capabilities extend to the solar system as well, and Io is, in infrared terms, one of the most luminous objects in the Jupiter system because Io is covered in fire. When Webb turns its mirror toward Io, it does not see what your eyes would see: the yellow and red and white and black patchwork of sulfur and lava and sulfur dioxide frost. It sees heat. It sees the glowing signatures of active eruptions, concentrated hotspots of infrared emission marking where the molten rock is closest to the surface or actively erupting. It sees Loki Patera, that 200-kilometer lava lake, burning brightly. It sees other active volcanic features scattered across the surface, and it sees something that no other telescope can match: chemistry. Webb is an instrument of extraordinary spectroscopic precision, meaning it can break the light it receives into individual wavelengths and read the fingerprints of specific molecules in that light. Every molecule absorbs and emits light at characteristic wavelengths, a barcode unique to each chemical written in the spectrum. From Io's volcanic emissions, Webb has detected signatures of sulfur, atomic sulfur, and its compounds, and of sulfur dioxide in various states. The SO2, that is Io's primary atmospheric constituent, and the sulfur-bearing gases that pour from its eruptions leave specific marks in Webb's infrared spectrum. So does the compound SO, sulfur monoxide, one sulfur atom bonded to one oxygen atom, which forms in the chemistry of Io's volcanic plumes and atmosphere. And among the signals Webb has detected are what are called forbidden emission lines, a precise term from atomic physics. A forbidden transition is not literally impossible. It is a transition between energy levels in an atom or ion that is extremely unlikely under normal conditions because the physics of the transition makes it slow. In the dense conditions of Earth's atmosphere, atoms collide with other atoms so frequently that these slow transitions are interrupted before they can complete. The atom gets knocked into a different state before it has a chance to emit the forbidden line. But in the thin, rarefied conditions of Io's volcanic plumes high above the surface, atoms have more time between collisions, and there the forbidden transitions can complete. The forbidden lines can be emitted, and Webb, with its extraordinary sensitivity, can detect them. This is not a small thing. The forbidden emission lines are a diagnostic tool, a way of reading the conditions in Io's plumes with a precision that is simply not possible with most other observations. The temperature, the density, the ionization state of the gas. All of this is encoded in the pattern of which lines are present and at what intensity. Webb is not just confirming that Io erupts. Webb is reading the eruptions. It is parsing the chemistry and physics of plume material that has been carried 500 kilometers above the surface and is now drifting in the near vacuum of Jupiter's radiation environment. This is what the headline means when it says, Webb looked at Io and found hundreds of volcanoes erupting at once. What Webb is seeing, and what the standing body of planetary science has established over decades of observation by Voyager, Galileo, New Horizons, Juno, and ground-based telescopes is that Io maintains this state continuously, not as an exceptional event, not as something that happened to be occurring when Webb happened to look. This is Io's normal. At any moment, more than 150 volcanic centers are estimated to be active. The plumes are rising, the lava is flowing. Loki Patera is overturning its crust on its slow, roughly annual cycle. What Webb adds is a new window onto the chemistry and thermal structure of all of this, a view in infrared light with the spectroscopic resolution to identify specific molecules that was not available before. It is not that Webb discovered Io's volcanism, it is that Webb is showing us what Io's volcanism is made of in ways that older instruments could only gesture at. The telescope that was built to look at the dawn of the universe is also, as a secondary capability, teaching us things about the fires of the most volcanic world in our own solar system. There is something satisfying about that. The same instrument that looks backward in time to the first galaxies can look sideways at a moon of Jupiter and read the spectrum of its sulfur plumes. So we have Juno flying low and close, returning the first high-resolution images in over 2 decades. We have Webb reading the chemistry of the eruptions in infrared, and we have decades of data from Galileo and Voyager beneath it all, building up the picture slowly, observation by observation, flyby by flyby. The picture that emerges is of a world in constant, violent thermodynamic conversation with the universe around it. Not isolated, not static. Receiving energy from Jupiter's gravitational field, converting it to heat through friction, routing that heat outward through a partly molten interior, erupting it at the surface through hundreds of volcanic vents, blasting it into the sky as plumes 500 kilometers tall, losing a ton of material every second to space, feeding a plasma torus. Lighting up Jupiter's aurora, energy in, energy out, all of it flowing through Io without pause, without rest, without a moment of geological quiet. Io does not rest. It cannot rest. As long as Io is in the 124 Laplace resonance with Europa and Ganymede, and that resonance has been stable for enormous stretches of time and is expected to remain so for the foreseeable future of the solar system. The tidal squeeze will continue. The orbits will remain slightly elliptical. The tidal bulge will keep shifting, the flexing will keep generating heat, and the volcanoes will keep erupting. This is the last piece of the picture, the synthesis, the place where everything that we have talked about, the history, the mechanism, the volcanoes and the plumes and the mountains and the plasma torus and the recent observations, comes together into something that you can carry forward. Io is what happens when a rocky world is placed by the accident of orbital dynamics in a gravitational resonance that will not let it settle. It cannot circularize its orbit. It cannot lose the eccentricity that Jupiter's gravity presses on it and the sibling moons sustain. It is caught between forces that will not release it, and the consequence is perpetual interior heat, perpetual volcanism, perpetual resurfacing, perpetual youth. There is a reading of Io's story that is simply one of violence, a world condemned to burn. And there is something to that reading. The mythological Io, the mortal woman tormented by Hera, persecuted across the world, unable to find rest, pursued and transformed, is not an accidental parallel. The people who named this moon chose well, or perhaps the universe arranged things neatly. But the other reading is this. Io is also a teacher, a living, burning, continuously operating laboratory for processes that once shaped the inner solar system and that still shape worlds we have not yet found. The high-temperature lavas of Io, possibly reaching 1600 Kelvin and above, hotter than any basalt erupting on Earth today, echo the kind of volcanism Earth experienced billions of years ago when the planet was younger and hotter and its mantle was producing the ancient, high-temperature lavas called komatiites. Those lavas have not erupted on Earth in over 2 billion years, but they are erupting right now on Io. In a very real sense, when we study Io's volcanic chemistry and heat flow, we are studying what Earth's volcanism may have looked like in its youth. Io is a window backward in time. Not a window to Earth specifically, but a window to the conditions and processes of a hotter, more energetic, more violently volcanic solar system interior, the kind of world the inner planets may have been in the first billion years. And then there is the forward-looking reading, the one that reaches toward what tidal heating might mean elsewhere. You know about Europa because this story has been leading there, gently, for a while. Europa, the second of the Galilean moons, slightly smaller than Io, farther from Jupiter, covered in ice. Europa receives tidal heating too, less than Io because its distance from Jupiter is greater and its forced eccentricity, maintained by the same Laplace resonance, is smaller. But enough. Enough to keep liquid water warm and fluid in the dark beneath that ice shell, possibly for billions of years. An ocean that has never seen sunlight, an ocean that, for all we know, has been sitting in the dark, warm, in contact with rock, with the chemical gradients and energy sources that life as we know it requires. We do not know whether there is life in Europa's ocean. We do not know enough about what life requires at the limits of its tolerance to make that claim with any confidence. What we know is that the conditions, liquid water, chemical gradients, sustained energy sources, long time scales, are there. The same force that is currently producing the most violent volcanism in the solar system is, at Europa's distance, producing a warm, liquid water ocean. The same orbital resonance, the same Jupiter, the same physics, and Europa is not the only one. Enceladus, the small moon of Saturn, is also tidally heated, in its case by Saturn's gravity and the resonances of Saturn's moon system. Enceladus is erupting water-rich plumes from its south pole, cracking through its icy crust, and those plumes have been sampled by the Cassini spacecraft, which found organic molecules, silica nanoparticles indicative of hydrothermal activity, and molecular hydrogen, the kind of chemistry that feeds life at deep-sea hydrothermal vents on Earth. Tidal heating, the same process, expressed in icy moons rather than rocky ones, producing warm water rather than lava, but driven by the same physics of orbital resonance and gravitational squeezing that fills Io with fire, hell and habitability, one force, many outcomes. This is perhaps the deepest thing Io teaches us, the thing that makes it not just a spectacular curiosity, but a genuinely important object in the story of how we understand the solar system and the possibilities of worlds. The energy source that makes life possible somewhere does not have to come from the star. It does not have to be sunlight. It can come from gravity. It can come from the mechanical energy of orbits, from the mathematics of resonance, from the accident of where a moon ended up, from the patient, endless, trillion-watt squeeze of a gas giant's tidal field. Io is the extreme end of that force, the end where the energy is too much, too hot, too violent, too continuously renewed. But further along the spectrum, at other distances around other bodies, the same force can be gentle enough to melt ice without boiling it, warm enough to sustain an ocean without evaporating it. The universe, it turns out, has more than one way to keep a world warm, and the same physics that makes one world utterly hostile to the biology we know is the physics that, in a gentler expression, may be creating the conditions for biology we have not yet met. Settle into that thought for a moment, if you are still with me. Wherever you are right now, in your bed, in the dark, with a lamp still burning somewhere nearby, or on a train moving through the night. You are on a planet that keeps itself warm in the old-fashioned way. Radioactive decay in the mantle. Residual heat from 4.5 billion years ago, still slowly seeping outward. The sun, of course. Ordinary warmth. But there are moons out there, orbiting giants far from the sun, that are kept warm by being squeezed, by the gravitational tug of a planet so massive that its very presence in space deforms the moons around it, cycling that deformation millions of times as the moons orbit, converting the energy of motion into heat, the way a paperclip bent back and forth generates warmth at the bend. Right now, as you drift, Io is erupting. Multiple volcanic centers are active, plumes are rising. Perhaps right now, in this moment, as you breathe, 500 kilometers above Io's surface, there's sulfur dioxide snow falling back in slow arcs to paint the plains in colors that should not exist on a rocky moon. Loki Patera's vast lava crust is moving slowly, tipping, foundering, overturning. The Eoplasma Taurus is revolving around Jupiter, glowing in ultraviolet that no eye will see. The flux tube is carrying millions of amperes between Io and Jupiter's poles. And somewhere in Io's auroral footprint in Jupiter's sky, the mark of a small volcanic moon is written in light. And Webb is watching. Its golden mirror, unfolding in space 1.5 million kilometers from Earth, is collecting photons that bounced off Io's volcanic plumes, sorting them by wavelength, reading the spectrum of sulfur in fire. Juno is watching too, its orbit bringing it around and around Jupiter, occasionally skimming past Io in those extraordinary close passes, returning images of mirror-smooth lava lakes and mountains thrust up from their own burial. We are paying attention. After 4 centuries, since Galileo Galilei first saw the 4 bright points of light around Jupiter in January 1610, thinking at first they were faint background stars, then noticing they moved, then realizing they were moons, and that Jupiter was a center of motion that did not include the Earth, we have sent our instruments and our mathematics into that system and have begun, slowly, to understand what it is. Voyager 1 in March 1979 made the first close pass, and the images came back showing an alien world, orange and red and white, erupting. And the people who had done the mathematics, Stan Peele and his colleagues, who had published their prediction just days before, almost in time to hear whether they were right, must have felt something extraordinary when those images arrived. The solid confirmation that the squeezing was real, that the volcanoes were there, that the math had looked ahead of the spacecraft and found something true. That moment, the paper published, the confirmation arriving almost simultaneously, is one of the small, clean stories that science occasionally produces, where the reasoning and the reality meet, and there is no gap between them. Io is not a comfortable world, but it is, in its blazing, sulphurous, electrically charged, perpetually erupting way, a remarkable one, a world that should not be able to maintain this level of geological activity. Too small, too old, its internal heat should have radiated away long ago, and yet cannot stop, because the energy that drives it does not come from inside. It comes from the relationship, from the resonance, from being in exactly the wrong orbit, at exactly the right distance from a gas giant massive enough to squeeze a moon-like dough, with exactly the right companions to keep the orbit from healing. The geology of Io is the biography of its position in the solar system. It is a story about relationships between objects, between Io and Jupiter, between Io and Europa and Ganymede, between the orbital mathematics and the interior physics, between the heat generated in the deep and the fire that escapes at the surface. You cannot understand Io without understanding the system it lives in. And when you understand the system, Io becomes not just a hellscape, but an argument that the universe has more ways to shape a world than we might assume. If you are still here, wherever you are listening from tonight, I want to close this gently. We started somewhere back at the beginning of this journey with a number, a staggering number, something on the order of 60 to 100 terawatts of power, generated continuously by a moon being squeezed. Several times the entire power output of human civilization, produced not by anything burning inside Io, not by the radioactive warmth that heats the Earth from within, but by the mechanical energy of orbital motion, of a moon moving in an ellipse, of gravity doing what gravity does. Pulling, flexing, generating friction, making heat. That heat has to go somewhere. And where it goes is everywhere on Io, up through the mantle, through the crust, out through 400 volcanic centers, into plumes 500 kilometers tall, across the surface in flows of lava hotter than anything erupting on Earth today, into a plasma torus around Jupiter, up the flux tube to Jupiter's poles, into auroral light. Io takes a force, gravity, the most ordinary thing in the universe, the force that holds you to the mattress you are lying on, the force that keeps the moon in its orbit above you, the force that gathered the Earth from a cloud of dust 4.5 billion years ago. And it shows you what that force can do when the geometry is right, when the resonance is right. When the masses and the distances conspire to make a particular moon the recipient of more tidal energy than it can quietly absorb. The most volcanic world in the solar system is not volcanic because of fire, it is volcanic because of math. And the same math turned down a little, pointed at a different moon, produces an ocean. Wherever you are listening from tonight, and I would love to know if you are still with me, what corner of the world, what time is it where you are? What does the quiet around you feel like? Wherever you are part of the same solar system that contains Io. You orbit the same sun. The gravity that holds you here, wherever here is the same force that squeezes a moon of Jupiter into perpetual fire. The physics is not exotic, it is the physics of everything. It is just that, out there, it is running at a scale and in a configuration that makes the consequences visible in a way that Earth's geology no longer shows us. There is something comforting, I find, in that. In knowing that the universe is not arbitrary, that the fire on Io follows the same rules as the tide that comes and goes on your nearest coast, as the way the moon pulls on the oceans, as the reason you feel a little heavier at the bottom of a hill than at the top. The same rules all the way down, all the way up, from the paperclip to the moon. If you found something in this tonight, if the image of Io's sky full of sulfur snow falling from plumes 500 kilometers tall found a resting place somewhere in your mind, then carry it gently into sleep. You do not have to hold every number, every name, every mechanism. The shape of the story is enough, the squeeze, the fire, the resonance that will not let it stop. The ocean next door kept warm by the same hand that builds the volcanoes. Hell and habitability written in the same equation. And if this is the kind of slow journey you like to take before sleep, then a like and a subscribe means more than you might expect to a small, quiet channel like this one. Small creators like me rely on your support to keep making things like this, to keep the narrations slow, the facts careful, the wonder intact. It helps enormously, and I am grateful for every person who has already subscribed and who comes back night after night to drift into sleep with a piece of the universe. Good night from up here in orbit. I'll keep watch while you drift.